I will, there we go, perfect. Okay, thank you very much. So today I'm going to give a brief summary of my PhD research, in which I'm trying to answer the question of airborne wind, will airborne wind energy systems scale? And if so, can they contribute to the decarbonization of the electricity grid? And a little bit of a preview and why I think it might be more beneficial for them to be a little bit smaller and might not even scale up all that much. And that is currently believed in the community. To answer this question, I will first start with a brief introduction on airborne wind energy systems in general, then talk about the methods I use to derive my wind data and the airborne wind energy model, followed by a brief analysis of my results, and then a summary and the conclusions. This will take about 22 minutes, and I'll gladly take the questions afterwards. So first of all, when I say airborne wind energy system, or AWES, I'm speaking of the crosswind system. Because of their highest energy power, this is the system or the design we focused on. And in comparison to a conventional three-bladed wind turbine, which you can see here on the left, AWES replaced the outer part of the rotor blade with a glider or a kite or a rigid wing aircraft that is then tethered to the ground. So basically replacing the main structural parts, that being the tower and the inner rotor blades, with the tether. Within crosswind AWES, there are two main sub-concepts. The onboard concept, or drag mode, which we can see here in the center, uses propellers for takeoff and landing. And then during the production phase, they are used to generate electricity aloft, which is then transported down via conductive tether. However, in my work, I'm focusing on the two-phase ground generation concept, or also called pumping mode. In this concept, electricity is produced at the ground station on the bottom, and which is connected to the glider aloft. During the production phase, the tether is reeled out from the drum, and as soon as maximum tether length is reached, the aircraft then goes back into its initial position and dives down and then repeats the cycle. Some of the benefits of AWES are that they have lower costs associated with them because of the reduced material, as they do not need the tower or the inner parts of the rotor blade, and they have a higher energy potential because they can operate at higher altitudes, which are presumed to be more stable and have generally higher wind speeds than at lower altitudes. And thirdly, they claim to produce less noise and have a less visual impact. However, there are still some challenges, and I'm going to cite a few of them here from a study from the European Commission. Generally, there are three main challenges here. One on the system side, being the aircraft, the tether, and everything combined. So the safety aspects, the performance, and the grid integration. Then also physical limitations. Generally, the wind resource is under-investigated, the land use of a farm setup, and thirdly, the administrative side, social acceptance of AWES, as well as the lack of regulations. And in my work, I'm mostly focusing on the performance assessment subject to more realistic wind resource assessment. And to do so, like a brief breakdown of my work. First, we investigated the wind resource using measurements and simulation, fed them into a AWES model to then assess the performance, in our case, the power curve, and as a performance index, we chose the AEP, the annual energy production. Now, starting with the methods. First, on the wind data, I collaborate with Fraunhofer IWES in Germany, where we gathered and analyzed wind data at an ideal wind location, which you can see here on the right-hand side. There's the LiDAR in the center. In the background, you can see the wind turbines. This is data gathered from a flat terrain in northern Germany. And for this, we used a pulsed long-range LiDAR with a horizontal range of about 4 kilometers. However, vertically, data availability decreased significantly. As you can see here on the right, from at 100 meters, data availability was about 80 to 90%, and that dropped dramatically to about 20 to 30% at 1,000 meters. Now, this is partially an inherent limitation of LiDAR remote sensing itself, because it relies on backscatter of aerosols that are transported with the air or with the wind. However, these aerosol particles generally originate from the surface and need to be transported aloft. So the aerosol load decreases with height. That being said, there are lots of other factors that still affect this, such as weather phenomena, cloud coverage, fog, and so on. Now, to overcome this limitation, I worked with the University of Oldenburg, who let me run mesoscale numeric weather research and forecasting models, in short, WRF model, on their supercluster. There we ran onshore and offshore WRF simulations with a duration of 1 year at a temporal resolution of 10 minutes, or at least we got data at a 10-minute temporal resolution, and therefore received a complete set of wind data. But in addition, we also got heat flux data, temperature and humidity, and so forth, which we then used to classify classify the wind regime. In terms of power estimation, there's a few steady state models, most notably Lloyd's formula, which you can see here. So Lloyd in the 1980s actually came up with the idea of crosswind kite power, and he derived the equation here, which still has a lot of assumptions in them. So, for example, it assumes a straight tether, neglects gravity, assumes a zero elevation angle, so a straight crosswind flight at zero elevation angle, and does not consider real-in energy consumption. Later, this got then improved upon by Schmel et al., who included misalignment losses, also called cosine losses, via elevation angle and azimuth angle. But again, this do not include tether drag losses or gravity. Now, one thing to keep in mind is that airborne wind energy systems generally never reach a steady state over the course of their power cycle, and which then leads to the conclusion that we do need a dynamic model. And to give you an estimate of how much power we estimate in comparison to Lloyd's formula, that was just about 50%, and that was during the production cycle, so not including the real-in power consumption. For the power optimization, I collaborated with the Systems Control and Optimization Laboratory at the University of Freiburg, who are developing the ARBOX, an Airborne Wind Energy Systems Optimization Toolbox, which formulates the periodic optimal control problem as a trajectory optimization problem to maximize average cycle power. It uses a direct collocation method, which breaks down the continuous trajectory into intervals. And since we have a highly nonlinear system, we need a good initial guess. And in our case, the initial guess is derived from a homotopy path initialization, which starts off with it simplifies the problem to a path following problem in the beginning using fictitious forces, then gradually reduces these forces to determine a feasible initial guess for the power optimization. The model itself is a 6 degrees of freedom rigid body model. It assumes a straight tether without tether drag. It is calculated at multiple points along the tether. The tether itself cannot be compressed, so it only uses tension forces, or is only constrained to tension forces. It's controlled via controlled surface deflection rates and the tether jerk. And best of all, it's validated against AMPIC's measurements. Now, AMPIC's also provided aerodynamic coefficients, which we can see here on the right in blue. This is the AP2 reference. And in our sizing study, we not only investigated these reference aerodynamic coefficients, but also high lift, which we can see here in orange. We compared the performance of aircraft with a wing area between 10 and 150 square meters, which resulted in a rated power of about 150 to 3,500 kilowatts, depending on system size and aerodynamic coefficient. Most importantly, we implemented a geometric scaling, where we assumed that the mass of the wing scales relative to the wingspan, which you can see here in the second bullet point. This B is the wingspan, and the mass scaling exponent, this kappa, varied between 2.7 and 3.3 to include beneficial and detrimental scaling effects. The tether was always sized to such that rated power was achieved at 10 meters per second wind speed. To recap, I used measurements and simulation to derive a more detailed wind resource definition, or to gather more information about the wind resource, used a dynamic aerodynamic AWES model. And then now I'm going to talk about the results in terms of AEP and power curve. But before this, I'm going to briefly summarize some of the wind results I found. Firstly, starting off with the wind resource assessment in terms of LiDAR. One of the things that we found is that there is a multimodal wind speed probability distribution, which you can see here on the right-hand side. On top for positive surface heat flux, and on the bottom for negative surface heat flux. And you can see that there are two distinct populations there, which once they're superimposed, make up the entire annual wind speed probability distribution. Positive surface heat flux on the top is more associated with typically unstable stratification. On the bottom, the negative surface heat flux is more associated with stable stratification with higher wind shear, whereas unstable stratification has lower wind shear and more constant profiles up to 1,000 meters more or less. And as a result, the entire wind speed probability distribution is better represented not by one Weibull distribution, which is the common representation for conventional wind, but at least two different ones. Now, we classified our WRF data using Obokov length, which solely relies on ground-based information, basically as a proxy for atmospheric stability, and found diverging wind profile shapes, which indicated an inhomogeneous stability with height, which is one of the reasons why we chose to use a purely mathematical clustering, here in this case the k-means clustering, to categorize our wind speed profiles by shape and wind speed. And as you can see here on the right, there's the results for the onshore and the offshore location. And below, we see the associated probability of the cluster centroids, or the average profiles within each cluster on the top. For our power assessment and the performance assessment, we did implement 3 different profiles out of each cluster to better represent the varying wind conditions. Here we can see a few selected results in terms of for the performance. On the left-hand side, we see the operating height in color, and in gray, the underlying wind speed profile which produces them. In the center, we see the side view of the corresponding trajectories. And as you can see here, most of the time, airborne wind energy systems operate below an altitude of 400 meters, and they usually only ascend to higher altitudes to depower, as this increases these cosine losses, so to say. Furthermore, one of the things that we can see is that the green trajectory is a little bit deformed, which is one of the things we found that happens quite frequently once the tether force constraint is active. On the right-hand side, we can see some time series. On the top, the tether speed, and on the bottom, the instantaneous power. And at low wind speeds, which are the blue and which basically the blue curve, or also the orange curve, we see that tether speed drops to 0, and as a result, instantaneous power drops to 0 as well for quite a long period of time, which is kind of detrimental when it comes to the grid integration of these systems, because usually the grid prefers a smoother power output. And this could be achieved via, for example, buffering of the energy or using multiple systems in a wind farm setup. Now, averaging over the cycle time and plotting the instantaneous power, or plotting the average power over reference wind speed, we can then derive the AOS power curve, which we can see here on the top for the onshore location in blue and the offshore location in orange, and also for both aerodynamic sets of aerodynamic coefficients, the high lift being higher performing on top and the reference case on the bottom. In the middle, we can then see the Weibull distribution, or the wind speed probability distribution at both locations, and multiplying both of them, the power curve with the wind speed probability distribution, gives us the energy distribution, and integrating over this then yields the annual energy production, the AEP. Now, finally, we want to compare the AEP for different sizes. And in this case, they are scaled with the lightest mass scaling exponent of 2.7. Onshore again is blue and offshore is orange. And for both aerodynamic coefficients. As expected, the AEP scales almost linearly with the wing area, but above 100 square meters, even for the lightest mass scaling exponent, we can see the negative effects of weight as it slightly decreases. And in general, the weight decreases the AWES performance. Now on the bottom, we now quantify the effect of mass compared to the lightest mass scaling, which we can see above. So these are showing the plots for a mass scaling exponent of 3 and 3.3 relative to a mass scaling exponent of 2.7 above. And what we can see here is that the system, the detrimental effect of mass, like it performs worse as it gets heavier. And this is particularly true for the AP2 reference cases, which are highlighted in, just show this here, so which are highlighted with a square, and what you can see here is that above a certain size, none of these systems converge anymore, which leads to the lack of data at that point. And what that basically means is that the aircraft is not able to produce sufficient lift to stay aloft while still producing electricity. Now that leads to the question, how heavy can these systems be, or the other way around, like what's the minimum lift that a system needs to produce to operate? And here we compare different average load factors. They're averaged over the real out, so the production cycle of the AOS. And that is to include the changes in the variation in lift, but also the variation in mass. As the tether reels out, we can increase mass over the reel out cycle. And as we can see here, during the average reel out phase, the AOS needs to produce at least 5 times more lift than its own weight to be able to operate. And this is comparable to the maneuvering load of an acrobatic aircraft, which has about a load factor of 6. What we found is that the limiting factor of the AOS operation is that during each loop, it needs to ascend, which leads to deceleration, which leads to a reduction of lift. And that's basically the critical path. Like within each loop of each cycle, it needs to ascend, basically. Right. So in conclusion, just briefly summarizing what we found. We found a wide range of wind speed profiles that lead to a multimodal wind speed probability distribution. And in general, wind conditions do not justify operating above 400 meters. And often higher altitudes are only flown to depower. And as a result, AOS are in direct competition with wind turbines, as the power curves are quite similar and the operating heights are not that much higher than conventional wind turbines. However, possible AWS deployment could be at high wind shear locations or at inaccessible locations to conventional wind turbines. In general, they would benefit from operating in a wind farm in order to smoothen out the grid integration, or possibly floating offshore wind, as the floating platform itself could be lighter than, or will be smaller and lighter than the one for conventional wind turbines. One of the things that needs to be kept in mind, however, is that the real implementation of AWS would definitely produce less power, as the results that I showed here are the output of a optimization process. And that is because some of these trajectories are quite maybe unrealistic, and in real deployment, they would probably fly more robust trajectories, which would produce less power. So coming back to our initial question, will AWS scale? Yes, but they need to stay within strict weight limitations, and are definitely constrained by the squared cube law, as aerodynamic forces, namely lift, increases with the wing area, whereas the mass increases with the volume. But before that, they are also limited by the limited wind resource, which is not strong enough to offset the increase in weight. Which is why I believe it would be more beneficial for AWS to have multiple smaller systems either operate in a wind farm setup, and they should definitely play to their, in my opinion, largest benefit, which is their mobility, which means that they can be deployed at different locations that are inaccessible to conventional wind turbines, or where conventional wind turbines are economically not feasible. In terms of future work, I would love to see a further investigation of the mid-altitude winds, which are the winds above 100 meters to 1,000 meters, to validate my findings, but also investigate the turbulence at these altitudes, because one of the claims in the community is that the winds are generally always less turbulent. And to do that, either investigation via LES or in situ or remote measurements would be interesting. The definition of a reference wind conditions would be great as well, because that would hopefully accelerate the development and the certification of AWS. And in terms, because thereby you could define reference load cases, for example. Another thing that would be quite interesting, because I just investigated a few representative designs, an actual design optimization would be quite interesting, basically building a design optimizer around the power optimization to then develop the real optimal design for a specific wind or reference wind. And lastly, now that I've investigated the performance of a rigid wing, it would be interesting to see how this compares to a kite system, for example, as kites are lighter and they scale better than rigid wings. Yes, they have less beneficial aerodynamic coefficients, but maybe the mass scaling offsets this. And the comparison to more robust trajectories would be more interesting too, because they would probably be more realistic than the findings here. Right, and before ending this presentation, I would like to acknowledge the help from Fraunhofer IWES and the University of Oldenburg, namely Ilona Bastigkeit, Martin Dörenkemper, and Gerald Steinfeld, who granted me access to their LiDAR data and the supercomputer to run the WRF simulations on. Furthermore, I'd like to acknowledge Rachel Leuthold, Joachim de Schutter, and Thilo Bronnemeyer for developing the ORBOX and helping me setting everything up and the continuous development of the ORBOX. And I also would like to thank my supervisor, Corinne Crawford, who supported me over the last 5 years, and thank the committee for being here today and taking the time to evaluate my thesis. And lastly, thank you to the audience for your attention, and I will gladly take your questions. Thank you very much.